Hello everyone, and welcome to the second day of this online tutorial series, Quantum Matter Meets Topology. And we continue with our first speaker from the last session, Professor Saroj Dash from Chalmers University of Technology in Sweden. And he's going to continue his talk on spin-polarized electronic transport in semiconductors, graphene and topological matters. And so in the first talk, he gave an excellent summary and the historical perspective of the development of spintronics, highlighting phenomena like giant magnetoresistance, spin transfer torque, spin orbit torque, and the spin Hall effect. So he also focused on material systems, and that's very interesting, not only from the material science point of view, but also often we find many exciting and undiscovered physics in those material systems. So importantly, he laid the foundation for today's talk, which is going to be on mostly 2D and topological materials. So for those of you who are joining for the first time today and those who need a reminder, a bit of the rules. So we are going to take questions approximately every 20 minutes. And at the end of 50 minutes, there would be a 10-minute question answer break, and followed by a 10-minute virtual coffee break where you can go and have a cup of coffee and then come back. And the talk would be 2 hours in duration, so we'll continue till noon GMT. And if you have any questions, feel free to type it. You can type it in the middle of the session also. And if there are fewer number of questions, we can actually turn on the microphone and take questions from you. But if there are too many questions, we prefer to have it in chat. Just to remind that this talk is being recorded, and we are going to upload the recording in YouTube, where you can also rewatch the session. So, okay, I'll hand over this to Saroj now.
Yeah, thank you, Niladri. So this is my second talk, as Niladri mentioned. So I'll continue to explain what we can do with the spin in the 2D and topological materials. So yeah, that's we saw the metal and semiconductor spintronics. Today we focus on graphene and other 2D heterostructures. And the second part, so this will be the first part, the graphene and 2D heterostructures, first 1 hour, then second hour is on topological materials. So this slide I also showed in the previous talk. So, but what I added here that what are the developments happening in the spintronics community? So this actually is helped by discovery of new materials. For example, these 2D materials, so they have excellent spintronic properties, and also you'll see the topological quantum materials also gives nice spin polarization. And so there is lots of actually 2D materials, as you see, graphene, 2D semiconductors, 2D insulators, magnets, topological materials, so semi-metals and superconductors. So as you know, for making a complete device, for example, if you want to make a metal oxide field effect transistor on semiconductors, so you need a semiconductor channel, you need a metal electrodes for the source and drain and contacts, and also you need gate oxides which having good interface with that means our insulator. So you cannot just make a complete device out of single material. You need lots of combinations. So if you go from 3D to 2D, you have to also look for complementary materials which you can use for your devices. So that will be highlight of this talk. So why these different materials are interesting? For example, graphene, as you know, they have at low energy this linear band dispersion, giving rise to a very high electron mobility and Dirac physics. And in the same time, you can use boron nitride, which is an insulator, together with graphene that you can use for encapsulation, tunnel barriers, and gate oxides, gate insulators. And also, molybdenum disulfide is a good semiconductor with a high spin orbit coupling, and they have a band gap. So they also have different values. You can populate independent with different kind of spins. And then topological insulators. It's not really 2D, you don't get, but you can make 2D topological insulators. So I'll show you today. Uh, then 2D ferromagnets. So the magnets with just monolayer can also survive. And you can get magnetism, antiferromagnets, ferromagnets, and different kind of properties. And finally, these different topological semimetals. So which have like Weil fermions or Dirac fermions. So let's start with graphene. So first, what I will show you that how graphene can be a good spin interconnect. So you heard about in the electronic circuit, there are interconnects which connects one device to other. They are mostly copper channels, or now they are using maybe some other metals depending on the electromigration properties or stability with thermal uh, treatments. But you need always a interconnect. So why graphene can be a good material for spin interconnect. That's the focus of uh, this part. So as you know, graphene have this Dirac band structure. So this gives rise to means very high electron mobility for the charge carriers. And also in addition, they have very low spin orbit coupling. And so the scattering is very much reduced. And this gives rise to very long spin diffusion length, more than 10 micrometer, and spin lifetime can be nanoseconds. Yeah. So I think we discussed all these mechanisms in the last lecture. So here, uh, all this nuclear fine interaction, uh, economical mechanism are very minimum. So whatever you get mostly are from Elliott effort mechanism if you have some impurities. So if you have non-magnetic impurities, for example on graphene, so it will scatter electrons. So that's why it's important to get very clean graphene to study its properties. So I'll show you some of these aspects. So you can find lots of review articles from when actually the first experiment showing spin transport in graphene was in 2007 by Bart Van Wijs group in Netherlands, where I did my postdoc after these developments. And there are lots of review articles you can see. So what is the main idea? So it remains the same as the field is developing. So how to create spin polarization first, then transport them. So now we can look at the length scale. So we want more than 100 micrometer spin transport so that we can communicate from one place to other with this. So it can be like a spin interconnect. So then we should be able to be manipulate the spins by electric field. So that's what we have to look for. And this also I motivated you, this how to make spin logic operations. So let's say, for example, you need a channel material, which is a spin interconnect, and you have these nanomagnets sitting here. You want to connect from one nanomagnet to other. So they are memory, the magnets are memory elements. So you want to connect them so that you can pass the information from one place to other. So you can store information at one place with the magnets, and you can communicate with the graphene or metal channels. So what I'll show you why graphene can be interesting for such applications. And you can, of course, do all the logic operations as shown in this paper. Actually, this paper was initially for semiconductors, then it developed for graphene. So there is not much change because most of the things happening actually in the nanomagnet side. So graphene just acts as an interconnect. Okay, so I'll show you how we are developing such a spin interconnect. So exactly we'll see such a graphene stripe we make, and we have these ferromagnets, and we try to connect them together. To start with, so some graphene properties. So you know graphene have a Dirac band structure. So when you apply a gate voltage, so you can go from electron doped to hole doped regime. So this is the resistance of a graphene channel with gate voltage. And you see such a Dirac type curves. So it's called Dirac curves because it have a maximum when you reach the Dirac point. And below this Dirac point, you have its hole holes are the carriers, and above that it's electrons as the carrier. And this is actually, I start with a large area CVD grown graphene, because if you want to make a interconnect more than 100 micrometers, so you need to look for large area graphene. And so we published in 2015 that we can show very long distance spin transport. So this graphene is commercially available. You can buy it from a market, and you can transfer on a 4-inch wafer. It's a big wafer, and then you can take a small piece to do your experiment. But it's a wafer scale graphene. So what you see here is a graphene stripe. And so you put this ferromagnetic contact. So it's a titanium oxide, 1 nanometer, just acts as a tunnel barrier. And then there is a cobalt around 50 nanometers, so to inject spins. So they are done by electron beam lithography, as you see, because the contact size should be very small around. It's like you want to make it a single domain so that you inject only one type of spin. Okay, so the device cross section looks like this. So you have this cobalt ferromagnet, you have little bit of titanium oxide around 1 to 2 nanometer. So you want to inject spins from the cobalt into graphene. So they actually get accumulated and they diffuse everywhere in the graphene. And what you do is you put another detector here, which is in a non-local geometry. So it's actually the charge current is flowing on the left side of the device, but in the voltage detection happens on the right side. So there is no charge current flowing. So only spins diffusing into the second electrode should be able to detect the um, spin potential here. So how the spin potential look like? So this is the spin-dependent chemical potential you create in graphene by injecting spins from cobalt into the graphene. So this spin chemical potential is splitted, as you see in graphene. But with the distance, as I discussed in the last lecture, so they will decay exponentially or any kind, so they will decay. So I'll come back to this picture because there was a question also in the last lecture. So what happens to the spin transport when we go from diffusive to ballistic regime, or if spin coherence length is very long? So that will change the picture here. But if you put the contact here, you can detect the spin chemical potential. When you are in the parallel configuration, you see this voltage. When you are in anti-parallel configuration, you see this down spins. So this voltage. So then you will see such spin valve signals. So this is for the parallel, you have this voltage range here. So this is become a resistance. So voltage divided by the supplied current. So what you see is this change in the resistance here, because you are measuring uh, chemical potential, the spin chemical potential for the off spin and down spin in these two cases. So this is the what you see, the normal, it's called spin valve measurements. And this is done with length up to 16 micrometer actually. And you know that we use a CVD graphene. So CVD graphene mobility is very low, around 2000 centimeters square per velocity second. And so the electron diffusion and the electron lifetime is very short. It's around in it's femtoseconds. Because it's a low mobility graphene, because it's a CVD graphene. So it should have lots of grain boundaries. So you don't see it here. You have to do a transmission electron microscope to see the grain boundaries. But because this is so long, we should have grain boundaries. I'll come to that grain boundary picture. So what we can do, as I told you in the last lecture with the metal spintronics, so you can apply a perpendicular magnetic field while doing these experiments, and spins will precess with Larmor frequency. So you get this line shapes of the resistance with magnetic field. So that is called Hanley spin precession. And we also developed the spin diffusion equation, as you maybe remember from last lecture. So this is the diffusion part, this is the precession part, and this is the dephasing. We don't have any drift because we don't apply electric field along the channel. So electric field is only happening in the left part. And the spin lifetime is in nanoseconds. So that's quite good for CVD graphene. because we have lots of defects and grain boundaries. And this is also on silicon oxide substrate, because that silicon oxide substrate can also affect the spin lifetime, because silicon oxide have lots of impurities, defects, dangling bonds. So there is lots of inhomogeneity in graphene. And in spite of that, you get very long distance up to 16 micrometers spin spin diffusion, and the lifetime is in nanosecond. Okay, and what one can study that we wanted to further improve that spin transport, and it took a little bit time because we have to improve the quality of our devices. So you see, after 5 years, we could report up to 33 micrometers spin transport, which is quite good in these devices. So this is the schematic again, and the spin valve experiment. This is one example. So what you can study, how you study the spin transport. So you can make devices of different lengths, different channel lengths, so the between the source and drain. And then you find the magnitude of the spin signal and you plot with exponentially. So they should decay according to the spin diffusion theory. So you have the resistance, how this change, and this is the polarization of the contacts, polarization 1 and 2. So that is squared here. And this is the spin diffusion length, and this is exponentially decays with length. So if you fit it, you find the spin diffusion length here. And it's around 7 micrometer at room temperature. And also you can do this Hanley experiments as I showed you. So this is for very long spin transport devices. And as I told you that we want to make spin circuits so that we communicate spin from different branches. So this is the schematics, and this is a real device, as you see. So we have these ferromagnetic contacts and also non-magnetic contacts. So just to use as a reference contacts. And these are this yellow ones, the ferromagnets. So this is a hexagon-like, hexa arm-like structure. So what we wanted to show that if we inject spin from one branch, so we can detect in different branches at the same time. And what we can see is that how the spin signal develops. So because when you have this magnets are non-collinear, so if your spin goes straight, so you'll get very symmetric Hanley curves, like as I showed you, like this. So very symmetric Hanley curves. But if you detect the spins at this point at angle, let's say here it's 45 degree or 60 degree, then you will see the asymmetric components. So the asymmetric signal, so this is for the parallel one, you see this is the asymmetric signal, and this is for the anti-parallel one. And what you can find out from this signal, you can find out the components for the symmetric and anti-symmetric parts. Okay, and these are for different angles, 120 degree around and 60 degree. And if we do that, so we did a simulation how this signal should look like. So if you are injecting spin at one point and detecting at several angles, so your detector is at several angles situated on the graphene. So what you should see that how symmetric and anti-symmetric signal should change. So this information is required if you want to make a spin circuit, because you want to send spins at and the nanomagnets may be sitting at different angles in a circuit. So that is quite useful, and it also practically works. So these are the experimental data points we have here, and the lines are the theoretical fits. So that's quite good. Then there is other issues, and because we are our group is part of the graphene flagship, which actually trying to develop graphene for spintronic applications in the European Union project. So we are looking how we can find out different problems existing with the CVD graphene, especially because it's for scalable systems, we need CVD graphene, not exfoliated ones. So in some CVD graphenes, you can find there are multi-layer patches. For example, here you find it's a large area graphene over a wafer scale, but you will find around 10 micrometer or 20 micrometer of patches at many places, like single layer, bilayer, and tri-layer even. So there are multi-layer patches. So we wanted to see how spin transport takes place across this um, these heterostructures. And also in some graphene, so you see this some ripple-like structures here. So here also, actually there are some folds. So when you transfer the graphene, so graphene is first grown on a copper foil and then transferred onto a silicon oxide substrate to make these devices. And while doing the transfer, you get this lots of folds and ripples. And here, for example, we have a graphene with a fold around, let's say, 0.6 nanometer height and around 400 nanometer fold. And we wanted to see how the spin transport takes place across this structure and also in a device where ferromagnet is situated between this bilayer, trilayer, and single layer structures. And what we surprisingly find out, so what we did is it's called a spin dynamic experiment, so that we measure the Hanley effect. So spin precision experiment. So we are applying magnetic field. So spins are precessing. And then we do this at different angles. And by doing that, you can fit this, how you can find what is the anisotropy or some kind of things developing in the system. So because there are some systems where you will find lots of anisotropy in the spin relaxation because it can have high spin orbit coupling or something like that. But in graphene system, we don't find anything at room temperatures. It's very isotropic around 1, and that's quite good for spin interconnect. And to understand what is the mechanism for spin transport in graphene, so I showed you last time how the Elliott effort mechanism and the equinopial mechanism. So Elliott effort mechanism is directly proportional to the momentum relaxation time. But in equinopial, it's actually indirectly proportional to the momentum relaxation time because it's mostly depend on the this spin orbit coupling system, like from the inversion symmetry of the system. So what we can do, we don't know which component is dominant, so we can actually take both of them together. So this is the spin lifetime in total, and we take Elliott effort, equinopial, and Elliott effort both together. So if we put these numbers here and solve this equation, we will find a simplified equation here that how the momentum relaxation time depends on the spin relaxation time. So you can just plot this as it's shown here. And if you uh, fit these lines for different layers, single layer graphene and with bilayer graphene, and then the boundaries and tri-layer graphene and graphene with fold. So they have little bit of difference spin relaxation properties, but what you can find is that by fitting these ones, you can find out the strength of both Elliott effort and equinopial here. And as you see, so this is in millielectron volt, the equinopial. This is the momentum scattering around 1 millielectron volt. But equinopial, which is actually the inversion symmetry broken systems with spin orbit coupling. So for different layers, so single layer to bilayer, tri-layer, and the boundaries. So it's around in micro electron volt, hundreds of micro electron volt. So which is quite good for these systems. So that means we need much cleaner system to actually see clearly the spin lifetime of graphene. But this dirty systems also gives a good property. So also you will find a theoretical paper. So they also find that even if you have grain boundaries, so that actually deteriorates the charge transport property of graphene, but the spin transport wise, it's quite good. And they find the grain boundaries do not affect much the spintronic property unless they are getting magnetic. If you have, because grain boundary also accumulates lots of contaminations and things like that. So that have to be verified also experimentally. Yeah, so there was an interesting question in the last talk. What about the high mobility spin transport? Means when spin is not in the diffusive regime, but in the ballistic regime. And it's for graphene, it's very usual question when you have a good quality graphene where it's not quite ballistic, but it can be quasi-ballistic so that you don't have to then use the diffusive equation because this was the diffusive equation the resistance you see in the spin transport and how it depends exponentially on this length and spin diffusion length. And so this will fail in the ballistic regime. So in this paper, actually this was last year, has been developed how the ballistic regime should uh, how the spin transport in this ballistic regime will look like. And what they have done, just to, so you can look at this paper for details. It's a quite nice paper to understand. So you can take this Landau formalism here. And so there are different terms as you see. And the first one is about, so it's a nearest neighbor hopping in graphene. And the second term, this is delta U, is it's called Anderson localization potential. So then it's actually some degenerers in the graphene you introduce, because your graphene will never be perfect. So what they have done is put some practical parameters into the equation. And so J here is the magnetic deterror. So if you have, let's say, very small amount of magnetic impurities, even parts per million, that can also affect the spin transport. And the last term, this S dot B, is the G-man exchange when you apply magnetic field. So what you can do is that, so here you can take all these different terms, have different weightage, so they can calculate with that. So for example, if you calculate with, let's say, some magnetic disorder of different quantity, and maybe you can take 0. So what you see is so in the Hanless experiments, what I showed you, that you just see one peak and then a dip, then it's gone. But if it is ballistic or quasi-ballistic, so you should be able to see multiple oscillations. Okay, and there are some new features coming because it's a high magnetic field, then G-man can also contribute. There may be other parameters which influence this. So you can also calculate that with the different J parameters, which is actually this magnetic disorder. And that is quite useful to understand if we make such devices in future. And that's also quite challenging. I'll show you what are the challenges to get such ballistic spin transport. And continuing with this calculation, as you see here, so as you see, if there's a less magnetic magnetic impurity, so this is J is very less, around 15 here. So your uh, the signal, spin signal, this is the spin signal with a distance. So it's actually going linearly. But if you have a higher order of magnetic disorder, so it's exponentially. So that is the summary of the paper. So how to get very high quality graphene? So that is also uh, quite challenging. And from 2008 onwards, people already know that. So graphene is not very perfect. So what you see, graphene on silicon oxide, it have lots of disorders. And people have measured with Kelvin probe microscope that some part of the graphene is p-type and some part are n-type, as you see here. So this is n-type, this is p-type graphene Dirac bands. So, and especially within few micrometers, you see lots of electron and hole puddles. So it's called electron hole puddles. And when you do such experiment, you see that graphene is heavily doped. It's the Dirac point is not at 0. And when you sweep back, you see also hysteresis. So you never know where you are in the system when you are measuring. So the one thing one can do is use boron nitride. So boron nitride, maybe all of you know already. So it's an insulator, and it's quite lattice matched with graphene, and quite perfect insulator. But it don't have a dangling bond. So that is quite interesting. And I also worked with such systems, and we get very high mobility graphene on boron nitride. So boron nitride substrate. So it's a flake, and also there is a graphene flake here, and we put contacts here to measure this quantum Hall effect. So as you see, the Dirac point looks very sharp here, very close to the 0 here. Still, we have some doping because the top surface of graphene is open. So we just have the substrate as boron nitride. But we have to do some cleaning procedure here because graphene is not covered by encapsulated completely by boron nitride. So we have some annealing procedure to get this high mobility. So mobility we could get up to 200,000 at low temperature and 100,000 at room temperature, so which is quite good. And as you see, we see this quantized Hall conductance at very low magnetic field, or even at 1 Tesla, you see this quantized conductance. So how to get better spin transport in such graphene devices? So for example, this is um, work with boron nitride, graphene. So you see very long distance spin transport. So it's quite close to the CVD graphene I showed. So one can, so that's very interesting that the CVD graphene on silicon oxide substrate also can match the exfoliated high quality devices. So that is quite surprising and also can be useful. And then people have what this is with a substrate, and then people have done with a capping, so that first they put the ferromagnetic contacts, then put the graphene, and with which is encapsulated with boron nitride. So they find out that the solvents and contaminations also can affect the spin lifetime properties. And here they could show spin lifetime up to 10 nanosecond, actually, which is quite good. So how to get very high quality graphene? So that is more interesting if you want to do spin transport in the ballistic regime. So you need high quality graphene. So high quality graphene can be only obtained if you encapsulate graphene completely inside the boron nitride. So if this is the graphene, you have on both sides boron nitride. And then if you do that, you don't have any chance to contact from the top because boron nitride is an insulator. So you have to find a way to contact at the edge. And the edge contacts can be very useful because it have a dangling bond for the carbon here, and contact will can transfer electrons very well at the system. And this was first demonstrated in 2015, and this gives rise to very high mobility graphene. So this is a Hallbar, this is a van der Pau method. So this is a graphene boron nitride heterostructure device here. And you see this is the Dirac curve. It's a very sharp, very close to zero, so very low doping. And the mobility of this graphene, so this is the black line here. This is the device, graphene boron nitride device. Mobility can go up to very high at low temperature. And so it's, if you compare to other semiconductors with a different temperature, carrier density, so this is how it look like. And this is all at room temperature. So the high mobility can be achieved at room temperature. And so this, now you know what is the difference between the top contact and the edge contact. So to do spin transport in graphene with high quality in the ballistic regime, so what you need actually ferromagnetic 1D contact. So these contacts before were made with chromium and gold. So if you want to make spin transport, you want to make ferromagnetic contacts, but with the edges. So this is, for example, one ferromagnetic contact with the edge structure here. But so what we saw was the spin transport was a bit challenging because stray magnetic field also plays a role here. But recently also some papers show that there can be some spin transport observed. But it's not very high quality graphene yet. So still experiments are going on to find such high quality graphene. Okay, what can be other interesting things one can study with spin transport in graphene, but with high quality graphene? So as you know, last 2 to 3 years, lots of development happened with a magic angle graphene. So if you twist two graphene layers at a small angle, like 1.1 degree, so this is like 1.1 degree twist between the up and top and bottom layer of graphene, and this is then encapsulated with boron nitride with a high quality, then what you see is that the band structure completely changes. So instead of a Dirac band, at the middle, you see actually a flat band condition. Okay. And this is like an insulating state. So you get some band gaps. And most importantly, so it's a very tunable system. So it's actually correlated electron physics coming into the picture. So electrons behave differently in these systems. And as you change the carrier density, so in the same device, you can go from metallic to matte insulator, And so the metal one is called a strange metal. Maybe some of you know in the oxide systems, people talk about that. And also magnetism. This is the anomalous Hall effect, and it's a quantized anomalous Hall effect for some carrier density already. So this is a very tunable system and very interesting to investigate what happens to the spin transport in this system, because you get the strange metal, Mott insulators, superconductors, and also magnetic systems in only graphene bilayers and trilayers also. So the recent science paper, and there's also more papers coming. And there are actually many papers in the last 3 years about these systems. It's quite interesting. Okay, so if there is any questions, we can take it now. I
Yeah,
can
if you
see
have
the
any
chat room.
questions, I mean, either you can raise your hand and I can turn on the microphone, or you can put it in the chat section. I have a question to start with, just a quick one. So, in one of the slides, in the angle-dependent Hanley measurements, you showed a very interesting device structure where you have like parallel electrodes, ferromagnetic electrodes, and one at an angle. So
Yes.
when you apply the magnetic field, say for the parallel transport, uh, and do you change the angle of you possibly keep the angle of the magnetic field constant? So I think the slide before this one, where you
Yeah.
have the device structure, mm, the one before this.
Yes. This one.
Yes, yeah, the one at the top. I was wondering that when you have the ferromagnetic electrodes at an angle, uh, is there a chance that you create a domain wall in there, depending on the
Uh,
angle of the magnetic field?
okay, so when you do spin valve measurement, you can do that. So because this is in plane.
Mm-hmm.
But what we do actually, so the when you do Hanley measurement, actually it's a
Yeah,
very
that's
small magnetic field
mm,
with a perpendicular magnet. So
yeah,
that may not
yeah.
change any
That
magnetization.
won't change anything.
Mm.
But for your in-plane measurements in the spin valve, would it affect, or do you change the magnetic field accordingly, or you keep the magnetic field angle constant, and then you measure between different electrodes?
Yes, so the magnetic field angle here, the applied field is constant in plane. So
Hmm.
just sweep the magnetic field. And but you don't see the complete picture here because this is showing a projection of the spins, because this is at some angle, and
Right.
so whatever spins are at this angle, you will see that.
Okay. Okay.
So yeah, it's a projection of the spins you inject onto the detector magnet. You don't
Mm.
see the complete magnitude here. But in
Yes.
the
Yeah.
Hanley, you can see that. You
Yeah.
can see the complete magnitude. But it have different components like symmetric and antisymmetric component,
Yes. Right.
because it's non-collinear.
Hmm. Very interesting structure. Hmm. Any questions? If not, I think perhaps we can take it
Yeah.
around the 50 minutes or 1 hour break.
Yes.
Yeah.
Okay.
Okay.
Let me then continue. So I showed you how boron nitride can be interesting for encapsulation and getting high quality graphene. Also, the boron nitride can be a good tunnel barrier and also good for spin injection into graphene. So as you know that we use a titanium oxide tunnel barrier, so it's not very perfect and it have pinholes because you cannot grow very thin oxide layer on graphene. So the pinholes can also affect the spin transport or spin injection into graphene. So if we use boron nitride instead of titanium oxide, so this can be quite good. And this is, for example, a device with graphene with boron nitride as a tunnel barrier. So this is a single layer. Um, it have some patches. I will come back to that. And but it's a monolayer boron nitride mostly, and it's a CVD grown. So we transfer it and we then patterned it. So it's not a flake; it's a wafer scale. And we get very good tunneling, nonlinear IV curves. So when you go to high voltage, and we plot the zero bias resistance, and so this is not much temperature dependent. So its quality of the tunnel barriers are very good. But what about the spin transport? Actually, in this boron nitride, it's not only monolayer. We also find in some places there are patches of bilayer, trilayer like that. And that actually we could use in our device structure. So we could put one contact on a multi-layer boron nitride with graphene below, and in the other part, the contact can be on monolayer or without boron nitride. So we could make multiple devices. So what we see is a very good result when we have a tri-layer boron nitride at one point. So we get very good signal up to 20 ohms here. And if we translate that signal into the spin polarization of the contact, because we know the polarization of the contact for the single layer, and by doing different devices, also putting different contacts, because as you see here, we have different contacts, and you can find out spin polarization of each contact by comparing with similar resistances. So the polarization with the multi-layer comes out to be 65%. So which is quite large. So here I compare the polarization. So this is the resistance of the contacts, and this is different devices. So it's a transparent contact without boron nitride, with titanium oxide. So you get 5%, but single layer boron nitride gives around 10% spin polarization. But if you are multi-layer, so you go to 65%. And this comes from the magnitude of the signal, what we see. And interestingly, this boron nitride tunnel barrier can be used for different applications. For example, here magnetic tunnel junctions. And here, the two ferromagnets can be separated by just a single layer of boron nitride or a molybdenum disulfide. So boron nitride is an insulator, MOS2 is a semiconductor, but still have a gap. But boron nitride should be a good tunnel barrier for spin injection into for the use of magnetic tunnel junctions. It's not only for magnetic, but also superconducting tunnel junctions and other applications. So such things can be used. Okay, so summary of this part. So I showed you how graphene is a good material for spin transport with different spintronic architectures, and the spin dynamics is quite uniform in these samples, and also these magnetic tunnel junctions with boron nitride and spin injection into graphene with boron nitride. But then graphene is a good material for spin transport, but how to manipulate spins? And for that, I'll show you how we can, you can take a such device, and then wherever you like, you put other 2D materials with their functional properties. You can change the properties of graphene. So I'll show you two examples. So one is the spin orbit proximity, and other is the magnetic proximity. So first, the spin orbit proximity. So as you know, graphene is having Dirac band structure, low spin orbit coupling in pristine graphene, and it should be around 10 micro electron volt of spin orbit coupling. So that gives the long coherence length. But as you know, if you have spin orbit coupling in graphene, maybe you can explore lots of properties which has not been done with graphene. No? So that can be quite interesting. For example, you can go from spin Hall effect to quantum spin Hall states or quantum anomalous if you have both spin orbit and magnetism. So there are lots of interesting things you can do with graphene. And maybe you can make graphene a topological insulator, because topological insulator was first proposed with a graphene system, but graphene have very low spin orbit coupling. So it was not possible to realize that. But I think now time has come to look for that again. So how to induce spin orbit coupling in graphene? So lots of experiments have been done to put some metals like platinum or heavy metals on graphene to induce spin orbit coupling. But that didn't really came out well because it also degrade graphene properties. So what is a good idea is that developed in many theory papers first, that when you put a graphene with a 2D material like MOS2 here, So it's a van der Waals force, so you are not affecting much the graphene electron mobility, but what you can do is that due to proximity, yeah, so you can open a gap. And if you increase the spin orbit coupling in these systems, what can happen theoretically is that you can create the spin splitting of the bands. And if you increase further, so the band should invert and it should be a topological insulator. Okay, so maybe we are in this regime, but people also have shown you can do such topological materials with spin orbit coupling. So this I'll show you such device, and we did this experiment, and in that time also lots of paper came out in this field. You can have a look. So what we do similar spin transport experiments. As you know, spins are very sensitive to spin orbit coupling. And so we inject spins from this electrode. So spins are diffusing in this heterostructure, which is a graphene with a MOS2, and we want to detect the spin at the other side. So while spins are coming in this heterostructure area, how they interact, we can find out. So this is a comparison. This is a pristine graphene, as you saw, see that is a large signal in ohms and spin lifetime around 500 picosecond in the pristine graphene, or it can be 1 nanosecond, but in this device it was like this. But when you have a heterostructure device, the spin signal is quite small, around in milliohms, and spin lifetime is 36 picosecond here. So this reduction can be due to different things, but it can be also due to proximity induced spin orbit coupling. So if we assume proximity induced spin orbit coupling, so we can find out that Elliott effort mechanism, which is due to momentum scattering, remains almost same, but the spin orbit term, the economically, which actually went up by orders of magnitude. This is one for only graphene, 0.1 millielectron volt, and for the heterostructure, is around 1 millielectron volt. And this is also supported by theoretical calculations, which actually estimate similar order of magnitude. And most interestingly, what we see when we apply a gate voltage, we can reduce the signal. That means it's tunable, and the signal magnitude can go down. And this is like an on and off. So it's not a spin transistor, but it's like you control the spin signal in some way. And also we could do the Hanley spin precision experiments where the signal strength is going down. Also the lifetime comes down. We can estimate the spin lifetime here with the gate voltage. So the signal goes down. Then we cannot actually see the signal. So we cannot estimate any lifetime. So, and why this is happening, we thought about that. And there may be two things happening together. So first, when you put MOS2 on top of graphene, so actually you induce a spin orbit coupling. So that reduces the overall spin signal due to spin orbit coupling. Then on top of that, when you apply a gate voltage, what can happen because your MOS2 is a semiconductor, because the semiconductor is turned on when you apply a positive gate voltage, it's an N-type semiconductor. So this is the log scale plot of this same. And again, another thing, between graphene and MOS2, there is a Schottky barrier. MOS2 is a semiconductor, graphene is a metal-like, but it's a tunable metal. So when you apply gate voltage, you tune the Fermi level in graphene. So you are going from valence band to the conduction band. And when you do that, actually, you are changing the Schottky barrier height between graphene and MOS2. And so Schottky barrier height between graphene and MOS2 goes from, let's say, 300 millielectron volt to almost 25 millielectron volt. So at room temperature, so there should be no barrier. So two things happening is that here you increase the conductivity of MOS2 when you apply gate voltage, and also reduce the barrier height between MOS2, so spins can enter into MOS2. So that also can reduce the spin polarization when you apply a gate voltage. So basically in this system, two things happening. One is proximity induced spin orbit reduces the spin lifetime. And when you apply a gate voltage, you actually allow spin to go into MOS2 so that you spin and get dephased. Okay, then I go to another system, which is actually a van der Waals magnet. So we wanted to induce magnetism in graphene by proximity. So what you have shown is graphene with MOF2 gives spin orbit proximity, and graphene with magnet can also give magnetism, means proximity induced magnetism. So these magnets were discovered in around 2017, and lots of activities going on here. So this is just from the review article I took, that there are different types of 2D magnets. This is chromium germanium telluride, chromium iodide, iron germanium telluride. So what you see, this is a insulator. So you have to do then some Kerr microscope experiment. So this is the Kerr rotation signal here, and how this TC changes with number of layers. So once you go to monolayer, the TC is very low, and for multi-layer, it's higher. So this is a insulating 2D magnet. And this is a chromium iodide is actually also a 2D magnet in monolayer. But when you go to multi-layer, it's actually antiferromagnet. Okay, so they couple antiferro. So if you see single layer is a ferromagnet with a hysteresis loop, like it's measured with again Kerr microscope because it's a semiconductor. Uh, when you go to bilayer, actually it's behave as an antiferromagnet. So you don't see that hysteresis loop. But when you go to again tri-layer, then again magnetism develops. So it have layer dependent magnetism. So that's quite interesting. And finally, FGT, iron germanium telluride, is a metallic ferromagnet. You can directly measure anomalous Hall effect. And there is lots of interest in these systems. And some of the devices you can make, like you can make magnetic tunnel junctions with a 2 FGT and in between a boron nitride tunnel barrier. So boron nitride is a good tunnel barrier, as I showed you. And one can see very high magnetoresistance or tunnel magnetoresistance in these structures. And again, the chromium iodide is actually it's a antiferromagnet, as you know. In different, if it have different layers, here it's a bilayer structure, and because it's an insulator, you can do tunneling experiment through this. So it have two graphite electrodes, and they are looking for tunneling transport through chromium iodide. And you can see this change in the conductance with magnetic field when you go from when you align different layers differently, whether they are all up or all down, or when they are anti-parallel. Quite interesting. Also, in the heterostructure side, what has been done while we were looking at such systems, so people have done this chromium iodide with tungsten selenide. So tungsten selenide have this valley polarizations. So these are two valleys. But where due to proximity with magnet, you can split the valleys. That is also interesting. And recently, also just in December, one more paper came out that you can find topological superconductivity in van der Waals heterostructures. So it's a niobium selenide, a superconductor, and then you have a monolayer of ferromagnet. And this is a scanning tunneling microscope experiments where they find this red, green, and blue dots here, the data points here. So in the green one at the edges, they find the zero bias peak, and they attribute it to this topological superconductivity, because if you open due to proximity, you can make such things theoretically. So maybe further experiments will tell more about such systems. And what we did actually, you can look at the several theory papers. So we wanted to study what happens to graphene in proximity with a 2D ferromagnet. And this 2D ferromagnet is chromium germanium telluride, which having Curie temperature around 80 Kelvin. And it is a perpendicular magnet. As you see, this is the perpendicular one, the blue one, which is preferred compared to the in plane, which is the red one. And we did similar experiments. So for example, we transport spins from graphene and they go through this heterostructure and we detect on the other side. So this is the Hanley experiment at room temperature. So this is the blue and the red curves. You see when you sweep up and sweep down, there is not much change. But when you cool down the system below 50 Kelvin, which is below the Curie temperature of the 2D magnet here. So what we see the splitting of the curves, and we could explain that with due to magnetic proximity effect. And that we see with the temperature dependence curves. So as you see, the splitting actually decays when you go to higher temperature. And we find surprisingly in the interface, actually, the Curie temperature is quite higher than the bulk sample. So that can happen, and people have found also in other systems that such proximity can also affect. And some recent developments also with graphene with EIG and graphene with these 2D magnets, some showing magnetoresistance. Here you see the anomalous Hall effect. And some theoretical proposals also interesting, how you can tune with electric field such exchange and spin in orbit interactions. So in the graphene, in one side, you can have a spin orbit interaction with tungsten sulfide, and on the other side, you can have a 2D magnet. So when you have both exchange and spin orbit interaction in graphene, so you can find some novel phases of matter. So for example, one can also go to the quantum anomalous Hall phase. Again, just to complete this part, so I show you some of the literatures recently people have done, and people how they try to detect the magnetic properties with graphene. So this is the proximity Zeeman spin Hall effect with graphene chromium bromide, and also platinum selenide is a semiconductor, but due to some defects, it also induced magnetism. In this paper, you can see. Okay, so the system have lots of opportunities in the van der Waal heterostructure, so you can combine any material together, but you have to think why we want to combine. If you have a good idea, it's quite easy to make such heterostructures, and you can find lots of varieties in these materials from different kinds. Okay, so with this, I summarize. I again showed you how graphene can be good for spin transport. And what other 2D material in heterostructure with graphene, you can induce spin orbit coupling and also magnetism. Okay, with that, I stop here and we take some questions.
Yeah, thanks, Saroj. Any questions? You can raise your hand or type it. So we'll have around 5-7 minutes of questions and answers, and followed by a 10-minute break, after which we are going to come back. I have one quick question for you. So when you're making this the thin film graphene sort of hybrid devices, what sort of issues do you face in terms of the interface degradation when you put the metal by? I think you use sputtering probably.
And you mean the metal contacts here?
The
No, this
metal
is by
contacts are
electron beam evaporation.
right.
If
Okay.
you sputter, you will degrade. Yeah.
Yeah,
So,
exactly. So that's what I was thinking.
yeah. So first thing is about the interface. For example, this graphene MOS2. So interface should be very clean. So nowadays we are actually using a glove box to put them together, and we make sure the interface of the heterostructure is cleaner. And then the contacts are all made by electron beam evaporation. So if you spot or deposit, yeah, so you have argon ions that can also damage.
Yeah. Okay.
Yeah.
There's one comment on the lecture uploading. So we will upload the lecture in YouTube, and I believe the link will be mailed later today, both the links for the last talk and today's talk. Since I still don't see any questions, another question for you would be, how much work has been done on the spectroscopy side, for example, using synchrotron radiation to detect spin orbit coupling in these heterostructures, or, for example, studying the 2D ferromagnets? Because one issue probably could be the size of the flakes that you get may not be sufficient for the signal to noise ratio.
Yes, yes. Yeah, that's a good question. So 2D ferromagnets, it's one need to grow by maybe MB. So then one need to encapsulate it somehow. So that is quite tricky part. And but I saw some papers with synchrotron RPS measurements on bulk van der Waals ferromagnet. For example, they just take the bulk material and cleave it and from the top and studied it. We are also doing some similar measurements in collaboration at Max Lab in Lund. And about other things, there have been some studies with graphene, and they then put some gold and other by evaporation and study what is happening in the RPS. And with the van der Waals heterostructures, so it's quite limited, as it is limited with the flex sizes, and one need actually this micro RPS, called nano RPS. So that will be helpful. But this graphene with a 2D magnet, so that will be a bit difficult to investigate because maybe you need actually graphene on top to protect the magnet to investigate in RPS. Because once you, because they are quite reactive, but the graphene with TMDs, MOS2, tungsten sulfide, so they are quite stable for few days. Yeah, so that can be done.
Yeah, I believe the similar considerations will also apply for studies like X-ray absorption spectroscopy, like XMCD or stuff. So yeah.
So whatever studies I see with XMCD, there is also now people are studying these magnetic materials, and it's on bulk magnets mostly.
Yeah. Okay.
Not monolayer. But monolayer, most of the studies are with MOOC because it's easier, and if it's the insulator, then that is the only technique. But with the graphene heterostructures, one can also detect with the proximity. For example, Andre Gaim and Nobeselov group, they are quite actively studying. I showed one of these papers. So what this is from Manchester. So you have this graphene hall bars. So it's similar structure as we usually make. They put a flake of chromium bromide. So there are some domain walls, and they could detect the magnetization of these domain walls from this Hall measurement. So it's a stray magnetic field which actually comes into picture with the graphene Hall structures. So here also graphene on platinum selenide, there is a graphene, and then platinum selenide, they detect the magnetism of platinum selenide with graphene. And similarly, what we do is yeah, so with such structure, so the magnetization and proximity effect can be detected by graphene.
Okay, thanks. Any more questions? Okay, if not, we'll take a 10-minute break here, and we will come back. So now it's 11:05 GMT. We are going to come back at 11:15. And then continue with, I believe this is the topological insulator part that you have next. Yes, so that will be the last part of the talk. So we'll continue with that. So, I mean, if you wish to leave the meeting, you can rejoin, but we'll keep the meeting on. Yeah, okay. Thank you. Thanks. Uh, shall we restart?
Yes.
Okay, so we'll restart the second session of the talk on spin-in topological materials.
Okay, good. Let's start again. So if somebody have questions, please write in the chat room, and either from this part of the course or from the other part of the previous parts. Okay, so next is going for topological states of matter. So as you see, the what happens in the topological states of matter that you when you have a huge spin orbit coupling. So we are talking about topological materials with spin orbit coupling. So there's a band inversion which can happen, and you can get different kinds of topological materials. For example, a topological insulator, which opens a gap, and you have this surface states. And also there can be while and Dirac semi-metals, so which having different properties, but they all give very nice spin textures. Therefore, it's interesting for spintronics as well. So for example, the graphene-like structure here, as you see, but it's quite different because it's coming from the internal spin orbit coupling. So the spin and momentum are perpendicular to each other. It's called spin momentum locking. Such phenomena can give rise to a spin polarization when you apply electric field. And also in the while and Dirac semi-metals. So this is like a electron pocket and a hole pocket here. As you see, this is called while node. And so this while nodes are actually connected by Fermi arc. This is the Fermi arc. And so many things here are spin polarized. So that will be interesting. So what you will see also, new kinds of Hall effect are emerging in these systems. So I think from 1879, as you know, Hall effect was discovered when you apply a perpendicular magnetic field and there's an electric field, and you get electrons to one side and holes to the other side. And in 1980s, the quantum version of this Hall effect was discovered, and it is because when you apply a strong magnetic field, you have this edge conduction, and inside it's the insulator because electrons are just moving around the magnetic field here. And in also after Hall effect, anomalous Hall effect was discovered in magnetic materials when you have a magnetization. And similarly, you'll see that quantum anomalous Hall effect was discovered in 2013 in a topological insulator with magnetic properties. Okay, then of course you have this spin Hall effect. It was proposed earlier but discovered in 2004 in gallium arsenide, as I showed you in the Friday's talk. And in topological insulators, it should be 2D, and its people have also observed quantum spin Hall effect in 2007. So this is quite interesting. As you see, lots of quantum versions of the Hall effect are emerging. So what is this? As you know, so here I show insulating state, quantum Hall state, and quantum spin Hall state together, and how you can simply understand that. So in the insulating state, you have a gap here. But when you go to quantum Hall state, so you have actually you apply perpendicular magnetic fields, which actually allow only the edge of the conduction to conduct, edge of the channels to conduct. It's having one state, which is actually called edge state. But when you have a but let me just emphasize what is the difference between quantum Hall effect and quantum spin Hall state. In the quantum Hall state, you don't need a spin orbit coupling, but you can use external magnetic field. But when you apply external magnetic field, you either apply a perpendicular magnetic field up direction or the down direction. So that gives one channel of these spins. But in a quantum spin Hall state, what you have is spin orbit coupling is acting as an internal magnetic field. And the spin orbit coupling for upspin and downspin, they are opposite. And internally, you actually created two type of quantum Hall effects. And if you combine these two quantum Hall effects with to be effective magnetic fields, then you get a quantum spin Hall state. And this is without magnetic field because the magnetic field is coming from the internal spin orbit coupling, for example. Just to keep it bit simple, so you can think like that. So how the topological insulators are developed? So what makes them, why we, in which materials and in which systems we can expect them? For example, if you don't have any spin orbit coupling, so you have a S level and P level. So this is the valence band, this is the conduction band. So this you call a band gap, no? So this is the band gap is defined like S minus P. But when you have a small spin orbit coupling, what happens? This P level is close to the nucleus, they split. So that is, but when you increase the spin orbit coupling with heavy elements like mercury telluride, bismuth selenide, bismuth telluride, there are now thousands of elements you can compounds you can find. So what happens? This P level can go above the S level because of the spin orbit splitting, and then this system is called inverted band. So band is, so instead of S minus P, you define P minus S. So it's an inverted band structure, and that is the origin of the topological insulators. So this is again a simplified picture. What happens? So this is the normal insulator. You have the conduction band, the valence band, and so this is at the boundary. So you see this chemical potentials are going up or down. But if it is a quantum spin Hall state, so the bands are inverted. So this blue line is above, going above the red line, and at the surfaces you have this states which is no more the insulator. So in the bulk you have to use the insulator, but at the surface it's conducting. So this has been proposed and also realized in 2007 by a group of Lawrence Mullenkamp in Germany. So this is the quantum spin Hall insulator state in mercury telluride quantum wells. So when you have a normal state, which is this, when the thickness of this quantum well, so this is a quantum well made from cadmium telluride, mercury telluride. So they do the band engineering to make such a quantum well so that you get high electron mobility. But because they have heavy, there are heavy elements, and if you change the thickness of these layers, so actually you also create the band modifications, and there is some strain in these structures. So that actually helps to enhance um, the band inversion. So in the normal state, when it's very thin layers, so you um, don't have any, you have a real band gap. But when you go to some thickness above that, you get some so the band inversion happening, and you see the surface states. And this is the red one, blue one, they have different spins. So this is like what schematically shown here. So what is the advantage that when you measure the resistance with gate voltage in such a structure with a Hall bar type of structures like this, so you see quantized conductance. So resistance is quantized, it's over 2e square, and you have two spins, so it's coming half of, so quantized conductance is 25, around 25 or 26 kilo ohm, and it's half of that. But you see, it's not very well quantized. So there are lots of noise in the measurement, and that is coming because the band gap you open. So let me go back one slide. So the gap, the inverted gap you open is very low, around 10 millielectron volt. And this is, you have to do very low temperature measurement because you have to stay in the gap of this band inversion. And also because of some impurities and things like that, so you don't get very good quantization. So the quantization, quantum Hall effect is actually very really flat. So up to 9 or 10 decimal, it should be flat, but here it's not the case. But this is a new developments, and maybe people will learn from this and develop new systems with larger band gap. So then after 10 years again, so people have found another system, which is actually a 2D material. It's a 1T prime structure of tungsten telluride. So this is the structure of that. It's a 1T prime in tetragonal structure. And then what happens, because it's a heavy element, tungsten, tellurium, So you should be able to open a gap here and the band should invert. So the gap here due to inversion of the bands is actually very large. And so people found out it to be order of more than 30-40 electron volts, um, 40 milli electron volts. And what actually resulted in this system, so this is the RPS measurement, this is the band structure. So as it's plotted here, you can see the similar kind. And also with the STM experiment, they see this gap. And more importantly, in the transport experiment with a whole bar type of devices, so what people have measured in 2018, this quantized edge conductance up to 100 Kelvin, because the gap you open is much larger, so you can measure also up to high temperature. But again, as you see, it's not well quantized. So it have lots of noise in the data because there are lots of defects and errors in the system. So that also can affect the properties of the quantized conductance. But still, there is not very good quantized system yet, and lots of research happening in this direction. Okay, then coming to 3D topological insulator, maybe most of you know that in the bulk material, bismuth selenide to tellurides, you can find that surface is conducting with spin polarized electrons, and the bulk is the insulator. So bulk is the insulator, but if you go to surface, it have these edge states, and this can be spin polarized. For example, spin momentum locking. So momentum and spin, they are 90° to each other. And this can be quite interesting for spintronic measurements. Also, people have seen with angle result photoemission spectroscopy and spin result spectroscopy also, you see this Dirac band structures. And when you measure the spin texture with spin result RPS, and you can find the polarization at different points here. And this is experimental data, so there is a little bit of deviations in different points. So around 75% polarization. So this can be quite interesting for spintronics for charge to spin conversion. So as we already discussed, that when a material is topologically protected and have some large Berry curvature, means it have a fictitious magnetic field inside due to spin orbit coupling. So they should give large spin Hall effect. Hmm. Also, from the band structure point of view, if you see there's a Raspa-Edelstein effect here. So if you have this huge spin orbit coupling, so in a semiconductor, so this band can split due to spin orbit coupling. And if you take a cut at any Fermi level here, so you get two bands. So this is the inner band, this is the outer band, and you apply electric field, you shift the Fermi sphere, so you actually accumulate these blue spins more than the red spins. And this spin polarization can be utilized for spintronic devices. And in the Dirac system, Dirac topological material system, it's actually the simplified version of this. So instead of two bands, you have only one band at the surface, and that is also spin momentum locked. And this gives the spin polarization. When you apply electric field, you create the spin density. And as I told you in the last lecture, so how people use platinum, tungsten, tantalum, heavy elements, and how industry is trying to develop such a spin orbit magnetic random access memory using these metals. But they are looking for these metals with high spin polarization. Hmm? And this is the limit which actually prohibits for the industrial application. Maybe it's one of the reason that you need a little bit higher current to create more spin polarization. But if you use such a topological material instead of these conventional metals, so you can create larger spin polarization, and that may help to develop these technologies. So here I will show you some of the results from our lab on the BSTS. And so this is a bismuth, this is an alloy of different elements, which actually gives more surface conduction than the bulk. And we could see Subnikov D-hash oscillations. And what we want to measure here is that we take such a material, a topological insulator, it's a BSTS, and then we have this ferromagnet. and we have this current source. So we apply current, and we are measuring with the ferromagnet what is happening here below the contact by this voltage probe. So what we do, we apply the in-plane magnetic field to switch the magnetization of this ferromagnet, and the spin direction in the TI we decide by applying the current. So when the current is in this direction, spin is like that. When current will be other direction, spin will be opposite because it's spin momentum locked. So that's what we see here. When we sweep the magnetic field, we change the magnetization of this ferromagnet. For positive 50 microamp, we see this switch, and then when you come back, we again see the switch. So this is a hysteresis loop like, and you can understand that by considering the magnetization of the ferromagnet and the spin direction. When you change the magnetization, the resistance changes or the voltage changes. When you change the current direction plus 50 to minus 50, you see this reverses. So that is as expected. So your spin is now down instead of up here. So we compared two materials because that is interesting to see from where the spin is coming, and so whether it's a surface versus ball conduction. So bismuth selenide, as you know, most of you know that it's a metallic material, so the resistance actually goes down with temperature, but BSTS is semiconducting in the beginning, the resistance goes up, and below 100 Kelvin, the resistance goes down. So in this is a good topological insulator material actually below 100 Kelvin. And above that, both also bulk contribution can be there. And we measured such signals in both devices. And now we plot the magnitude of the signal with temperature. So what we see in the bismuth selenide, actually, it's almost flat with temperature. But for the BSTS, the magnitude of the signal goes up below 100 Kelvin, where actually surface states actually dominating. So that means if we look at the literature, we find such a band structure already people have measured with spin RPS. And this is the schematics of that. So this is the Dirac band. And if you are here, the spin polarization what you get is will be very large. But if you are coming close to the conduction band, so Dirac surface states still dominate, still contribute, but also contributions from the raster bands in the bulk of the topological insulator can contribute. So this is how you can tune the properties. So people also have done some gate dependent studies to see what happens. But as you know, so it's very difficult to do the gate dependence because you have two surfaces and inside there is a bulk. So you don't know where you are tuning the, if you use a back gate and measuring on top, so the whole crystal will screen the back gate. So you will not see what is happening on the top. And if you have a top gate, that will be a bit helpful, but it just complicates the device design. Also, it's interesting to see how this can be useful. These topological insulators can be useful. So for the spin orbit torque and switching of the switching with TIs. So there is lots of paper in the literature already. So people have used bismuth selenide and BSTS, many kinds of compounds with MPE grown by spotter deposition, which actually gives not like a TI, but it's just heavy elements, polycrystalline samples. So they are also, they see very nice switching of the magnet. So this magnet on top of this topological insulator, they could switch with very low current compared to what we can do with platinum or tungsten. So this is quite useful for industrial application because it can be deposited by spotter deposition. So I just mentioned that it may be not a topological insulator, but this material helps to get high spin to charge conversion. And also people have seen how to also tune by thickness, by different topological insulator thickness. They can see the spin Hall angle. It's very large when you go to very thin samples. Okay. Then one thing I wanted to mention here because people put this permalloy directly in contact with bismuth selenide. But you know that when you have a surface state here of the topological insulator, there was a question in the last lecture on Friday. So what are the symmetries which have to be protected or broken to in this topological insulator systems? So for the topological insulator, you have to retain the symmetries. But if you apply a magnetic field or you deposit some magnetic elements on top of your topological insulator, or you dope it by some means, then actually you break the time reversal symmetry and you open a gap here. And then this gap actually, within this gap, you have actually one edge states which is actually coming up here. And what people see in such systems is that a quantum anomalous Hall effect. So this was quite a bit challenging. So first it was observed actually in chromium doped topological insulators. And because it was very limited to low temperature, then people tried this proximity effects. So people have different layers with chromium doping here and with just a Ti, bismuth Sb telluride. It's a multi-layer structure. So this is the quantum anomalous Hall effect, what you see. It's well quantized, but even it's at very low temperature. But it is happening with proximity now. Okay, so you have to break the symmetry to get this, go into this anomalous Hall effect. But if we consider for spintronic applications, so if you have a magnet and a Ti, so if you bring them together, then you can break the symmetry. Then the interface quality is not the same. So there are proposals. So how to get rid of that problem by putting a graphene in between. So it is also expected that you also improve the spin charge conversion by putting a graphene because graphene is a good medium for spin transport. And we have done that experiment by putting a topological insulator on top of graphene channel here. So similar to what I showed in the previous lectures. So we send a spin current in this heterostructure and try to detect on the other side. And we can see what is the spin orbit coupling when on graphene due to topological insulator. And there is a theoretical idea how what should happen. So you should open the gap in the graphene and some spin textures. So the spins near the Dirac point will be perpendicular, and away from the Dirac point, it's more in plane. So it's going from more Raspa type to perpendicular spins. And this was done in collaboration with Stefan Roos group in Barcelona. So this is again the experimental setup. As I showed, we pass the current here. So we inject spin into graphene from this ferromagnet. Spins is going under this channel and we detect the voltage. And this is how the spin signal look like. And this is what we see is that when we apply the gate voltage, so it's quite tunable and that can be coming from different experimental facts. So I'll not go into details. And but when we calculate the spin orbit coupling strength, so I showed you in the uh, previous part of the lecture how we calculate the spin orbit strength. So we combine Elliott effort and Econoper, and we use this formula, and we find the spin lifetime for different gate voltage and plot it here. So this is from the Hanley measurements. And this is for only graphene, and this is for the heterostructures. And we find again this Econoper mechanism, which is due to inversion symmetry broken in the system, which is a bit higher here. So that was quite helpful. Then we thought to make some practical device to use that spin orbit coupling. So what we did here is that we apply, we make a hall bar type of structure like this. So this is our graphene. So this is a topological insulator on top. And then we have different contacts. So this is a ferromagnet, the blue ones, and the yellow ones are titanium gold. So what we wanted to see, let's say we create such a spin splitting in the graphene, and we wanted to detect that. So the experiment looks like this. So we send a spin current from this graphene on ferromagnet on graphene here. The spin is coming, and we should be able to detect a voltage by this ferromagnet. And also we should be at the same time detect a voltage across this heterostructure. So when we detect this voltage V2, because this ferromagnet and this ferromagnet are not collinear, it's at an angle of 90 degree, we get this Hanley curves, which is asymmetric. And when we measure the voltage V with the in-plane sweep, so when we switch this magnet, we actually see this change in voltage, what we measure here. And when we apply a perpendicular field, also we see that spins are coming and precessing in the channel, and the voltage signal is also getting modulated like this here. So this confirms observation of both spin valves and Hanley confirms that it is coming from the spin. Then we thought to understand what is happening, we wanted to do the gate voltage dependence. So at minus 80 gate voltage, we are in the valence band. And at a plus 75 gate voltage, here we are in the conduction band. So as expected, what we see is because the spin directions are the same in this band here in the graphene, but we are dealing with electrons and holes. So this is for holes, this is for electrons. So that means the sign should change. So this indicates that spins are coming from the graphene band structure. So there may be many possibilities. So I can show you some possibilities one by one. So we can rule out actually if it is coming from the TI, because from the TI bulk states, actually it's a highly doped topological insulator. We don't expect any gate tunability. And we can also rule out from the surface states because we have some interface resistance between graphene and TI, and also what is expected that the sign also should not change if it is only surface states. And this, because if it is only TI, the sign should not change because it's just one band like this, so sign should not change. And what is happening, what can be happening is there's two things, either spin Hall effect or Raspberry-Edelstein effect in proximatized graphene. So because the spin Hall effect will give perpendicular spins, that what we cannot see in our measurement detection system because our cobalt, which is injecting the spin, is in plane. And but what we see is can be explained by considering the Raspberry-Edelstein effect because this is in plane spins, and this also should change sign as I showed you. Okay, so with this, maybe I can stop and take some questions.
Yeah, I think there's already a question in the chat.
Okay, let me check. I have basic question of how can we move from TI to Dirac semi-metal and vice versa in terms of symmetry breaking. Yeah, so this is my next slide actually. Let me, I have, yeah, there another question. I have a very basic question. Can we explain how very phase physically affect topological properties in some intuitive way? So so it's the first question. Let me answer. So, but I have to go to the next slide because the question is here already, and it was few times. So, for example, this is the exactly what you are actually asking. So, if you have a topological insulator, you can apply a magnetic field, and that will also change. It's a bit high magnetic field of a few Teslas. Then you actually go to the while states like bismuth. In the bismuth selenide systems and telluride systems, people have shown that experimentally. And for the other way around, so it's like a Dirac system. If you break inversion symmetry and or time reversal symmetry, you also can go to these wild states. So that is a simplified explanation. And yeah, about the question from about the Berry phase, how it is actually affects the topological. So yeah, maybe it will be difficult for me to answer that question because I didn't cover those basic things. Will that be okay if you can email me and I can send you some references and things like that? Okay, good. Yeah, just email me. I'll send you more details. Why are the RT plot of BSTs so different from bismuth-selenide? What does the hump saturation in? Okay, yeah, it's a good question. The basic thing is in a TI. So that yeah, the theoretically topological insulators, as you see, it should be perfectly like that. But in reality, that does not happen when you grow topological insulators. So the question is why bismuth-selenide is metallic? Eh? So you have some selenium vacancies when you grow them, and that gives the so your Fermi level is actually not in the Dirac band gap; it's actually in the bulk conduction band. So that gives the metallic nature of the topological insulator. But in the case of BSTS, so you are actually your Fermi level is in the Dirac band gap here, so it's below the conduction band. So, but some bulk conduction is also happening in the beginning. But because it's a semiconductor, so when you cool down, so you actually freeze out the bulk carriers because Fermi level is not there. So most of the conduction happening below the conduction band. And when you freeze out all the bulk conduction of the semiconductor below some temperature, so whatever remaining conduction is mostly coming from the surface states. So the surface state is more dominating in the transport. So therefore, you see this bump-like feature. So two mechanisms are competing at some temperature. Below some temperature, the surface is more dominating, and above that temperature, more bulk, which is actually freezing out when you cool down. So carriers are getting frozen. Yeah, I hope it's clear.
There's
So
another question.
yeah, can we make silicon a topological insulator? So for example, like people are trying with graphene um, to make a topological insulator. So what you need is a, so this is, so topological insulator can be many kinds, but what we are talking about here is mostly the spin orbit induced topological insulators. So you have to induce spin orbit coupling, and silicon is very weak with spin orbit coupling. So so for the example with the graphene, it's much easier to make maybe in future. And people have shown some evidence because you can, it's a single layer, you can put in proximity with a heavy tungsten selenides and things like that. So you induce a spin orbit gap in the system. But silicon, I think it may be challenging if it is bulk silicon. Of course, you can take silicon, like people are developing one layer of silicon atoms, but it's not very stable in air. So that is also challenging. But in silicon, there are many theoretical proposals. There should be higher spin orbit coupling, but one can also do some proximity effects. You can grow silicon on a heavy element. Maybe that will create something. It's possible, but lots of research are required, and maybe some of you have a good idea to do that. What happens to MR in BSTs? MR, I mean I think you mean magnetoresistance. So because so there have been many studies in with a magnetoresistance. So what happens, you will see many features when you do magnetoresistance. For example, this is the magnetic field perpendicular, and this is the resistance. You see a dip here. It's called weak anti-localization, and this appears with material with high spin orbit coupling. Then you go to a higher field. So this is a bit noisy data because it was a very thin flake. But if you measure bulk samples, you see very nice oscillations. So this is the oscillation what you see here after subtracting a background. This is called Shubnikov-Dihas oscillations. From there, we can find the mobility of the sample and also the carrier density. And with this, we can say where we are actually in the gap. So whether we are how much below the conduction band here. I hope I answered the question. Yeah, there's a hand.
There is, yes, I'll try and make it. Let's see. Okay, I will put you on microphone, so you should be able to ask the question directly.
Hello, sir.
Yes.
So I was asking that in the that BSTS resistivity curve, you said that above a certain temperature, the bulk states are responsible for conduction, and below the temperature, the edge state are appearing.
Yes.
Yes, sir, in this curve.
Yeah. So can you tell
So
the question?
yeah,
Yeah.
the question is, when we change the doping concentration, is the temperature is changed at which we are getting the bump, or the temperature below which the surface states or edge states are dominating in the conduction?
So your question is if we change the composition of this
Yes,
BFTS,
yes,
whether
sir.
this will change. Yes,
Yeah.
yes. That should happen. Yes.
Okay, sir.
So if you go, so people have, so we have not, because we actually work with single crystals and we don't grow the crystals ourselves. And we have very limited access to these crystals. So we focus more on the devices, but the people have done the careful composition dependent measurements. And that is what happening. So people see it's going from metallic to uh, uh, more towards the conducting, means like insulating phase, and you can make it N type and P type, so that can be done.
Okay, sir. Thank you.
Shall we take the last few questions at the end, or would you like to
Yes.
take it now?
Okay, we can take at the end.
Yeah, we'll make a note of this and we'll ask at the end.
Okay, so as we discussed with the topological insulators, there are also topological semi-metals, but you have to look at the broken symmetries in these systems. And recently there have been developments like Weil semi-metals and Dirac semi-metals. And particularly it's interesting because it have different physics and which is governed by Weil fermions instead of Dirac fermions. And why it's interesting for our experiments, so the spin polarization are not only limited to the surface states. So there is also bulk states in the systems which is also spin polarized. So that is much more easier for doing experiments, we thought, but it's again complicated because you have also contributions from surface, bulk, both together. But for practical purpose, so for some experiments or some applications, people don't care what is happening maybe in the beginning. If you see a larger spin polarization, so people, industry will be interested to use it. Maybe later on, people can try to understand what is really happening. So for example, I start with the topological semi-metal. It's called tungsten telluride. So it's actually, it can be T1 phase or T2, TD phase, depending on the temperature. And there is a calculation showing that, so there is a spin texture in this material. So this is the paper which I refer to. So there's a spin textures in these materials for this electron and hole pockets at the different Weil nodes. So this is very interesting because this material is a broken symmetry. And so it's only symmetric along these two planes, and other planes are having broken symmetry. And I'll quickly go through some literature, what people have measured in this tungsten telluride. So shows a very giant magnetoresistance up to 10 to the power 5 times in the bulk samples. So because it's a semi-metal. And people saw some negative magnetoresistance at some angles. And that gives like a chiral anomaly type of behavior. And I showed you already this quantum anomalous Hall effect in monolayers. And also with supercurrents flowing, if you have a palladium, which is a superconductor at low temperature. So people saw this Josephson current, which actually they find some components of these currents, which are actually confined to the edges. So this is like a edge currents, edge supercurrents in these structures. So quite interesting system, and this just developed in 2020. So I think after graphene, so this is the most interesting material people are studying. So we also see similar things in the, this is a bulk sample. And we also make this very thin layers up to 5 nanometer. And we see metallic conduction. And we also see the Subnikov D-hash oscillations with high magnetic field. So we can find out carrier mobility, so which is around 10,000, something around that at low temperature. So which is a good material. And with this, we wanted to study spin to charge conversion. And so we make a device like this. So we have a tungsten telluride on graphene. So we could inject spin from this and detect with graphene. So Niladri, I have a question. So we are actually very close to the time here. So can we go a bit beyond, or we have to finish exactly at?
No, that's fine. When you can continue.
Okay. Yeah, I made
Yeah, that
more
should be
minutes.
all
Yeah.
right. Yeah, sure.
Okay, so as you see, the device is here. So this is the graphene. Then you have tungsten telluride. We have this contacts. So we have both ferromagnets and non-magnetic contacts. So what is the experiment? So first I focus. So we observe two type of things here, and one is a conventional spin Hall effect. I say conventional charge spin conversion. CSC means charge spin conversion means we apply either a charge current or a spin current. We can convert from one to other. So here I saw one experiment where we actually send a spin current from the ferromagnet into the graphene. Then spin have to enter the tungsten telluride and we measure a voltage. Okay, it's a non-local measurement. So only spins entering there will be affecting the measurement. And then what we do, while spins are going, you will see some voltage signal which will change with if you change the magnetization of this magnet. But we did an experiment with the spin precession, as I told you earlier. So spins will precess. So that will modulate the signal like this. So from this measurement, we can know what is the direction of spins we are injecting or means. So we can know the direction of the spin polarization while they are entering the tungsten telluride. So this is as expected, as you see. So this is giving a conventional spin Hall effect where spin current and the charge current and the spin direction in this tungsten telluride are perpendicular to each other. Okay, so this is in this measurement geometry. And I should mention that in these devices, the interface resistance between graphene and tungsten telluride around in kilo ohms, a bit higher. So then when we change the magnetization of this, we can see that the sign changes. So this is for plus M, this is for minus M. So the sign changes and it behaves as it used to be. Then we also observe a unconventional spin Hall effect, which is due to a perpendicular spin coming where spin current and the charge current, they are actually parallel to each other. So the spin direction is perpendicular to this. So why we call unconventional? Because this is not expected in conventional materials. but it is possible in tungsten telluride because the symmetry is broken. So you can find other components of spin because of the broken symmetry. So what we see here is this is all at room temperature. So if we pass a current in tungsten telluride, so it actually creates a spin polarization just like a magnet. So you can inject that spin into the graphene and spin propagate in the graphene and you detect with the ferromagnet. So these techniques actually cannot be useful for practical applications maybe, but this is quite useful for studying a new material because you cannot do such measurements with other techniques. And also you see the spin valves when you switch the magnetization of this ferromagnet. And when you do a Hanley measurement with perpendicular magnetic field, you see this Hanley spin precession signal for both parallel and anti-parallel configuration. The green is the anti-parallel, means the ferromagnet is in opposite direction. And from this measurement, we estimate the spin polarization around 10% for tungsten telluride because we know the spin polarization of this ferromagnet. So in addition to the injection of spin from tungsten telluride, we can use the tungsten telluride also to detect the spin. So we send a spin current from ferromagnet into graphene and they enter tungsten telluride, and tungsten telluride detects a voltage which actually detects the spin as you see here, and both signals are reciprocal to each other, and even the Hanley signals also survives. So it is quite good for applications. Here also we cool down the sample to very low temperature, and up to 10 Kelvin we also see the signal, same signal, and that means the origin of the signal is the same throughout the temperature from room temperature to 10 Kelvin. But the signal is getting a bit noisier at low temperature. That is because the interface resistance between tungsten telluride and graphene is actually increasing at low temperature. So that actually contributes to the signal noise. But the magnitude of the signal, I would say, is not changing much. So that means whatever the spin polarization from where it's coming due to this spin charge conversion, it survives at all temperature up to room temperature. And this has been quite popular, this material, because whatever I showed with spin orbit torque type of experiments, so that is actually not very convenient for a perpendicular magnet, because for a high density integration, you need to integrate the perpendicular magnet for spin orbit torque. So the magnet on the whatever you use should have perpendicular magnetic anisotropy. And to switch a perpendicular magnetic anisotropy system, you need a out of plane anti-damping torque. So out of plane magnetic means spin polarization. And because tungsten telluride, as I told you earlier, gives a out of plane spin polarization, so that is quite good. So such system was not before, so not known before. So this is just after tungsten telluride came. So you have access to more low symmetry materials. So there is lots of research going on to look for different low symmetry materials to see for charge to spin conversion. So such systems has been used for spin orbit torque now, but it's all flex, so it have to be developed further if application is required. And also recently some archive papers in this direction showing that the tungsten telluride can be used to switch a 2D magnet. And 2D magnets are mostly perpendicular, like iron germanium telluride. This is tungsten telluride. So they make this van der Waals heterostructure. And by passing a current in tungsten telluride, you create the spin polarization, and you can then switch the magnet. And this switching property also can be done with a pulse current, and this is the temperature dependence because this magnet, iron germanium telluride, have a low Curie temperature. So this is limited to low temperature, but it should be possible if we find 2D magnets with higher Curie temperature. Okay, then I wanted to give some outlook about the such topological systems. And whatever I showed you in the experiments, actually, it's not a uh, final result set. So there is lots of development still have to be done. So as you know, topological states should give very large spin Hall effect or spin charge conversion. But we are not at the Dirac point or the Weil point. So our materials are highly doped. So for example, in the tungsten telluride, what I showed, we are not at the Weil point. So we are above the Weil points. So that we don't know what is the contribution of these topological states really. We cannot separate out. So that will be good thing to think about. Also, in some materials, like in type 1 topological Weil semimetals, like tantalum arsenide, so it have this Weil nodes. In type 2, it's actually tilted. And that will be interesting to see. And the number of Weil nodes in the system are many. Some have more than 8, around, it's multiple Weil nodes. So what people are looking for material with a minimum Weil nodes and closer to Fermi level and large separation between Weil nodes in momentum space. So this separation between these Weil nodes should be large so that it can be more tunable. So such examples also exist. So as I told you, the spin polarization of the bulk and Fermi arc is quite interesting for tantalum arsenide and tungsten telluride. So the tantalum arsenide results are measured already by RPS. Also tungsten telluride also measured by RPS. So this gives very nice properties. And what can be possible that you can tune the spin orbit coupling so that you tune the separation between these Weil nodes. So this is the one Weil point, other Weil point here, and there is a Fermi arc. So you can change the separation by tuning the spin orbit coupling. From niobium phosphide to tantalum arsenide, you change the spin orbit coupling, you see the Weil point splitting is also increasing. And so these are very interesting systems to study. And also, as I pointed out, so you can have this magnetic Weil points, and there are lots of developments with the antiferromagnets, magnesium systems, ferromagnets, cobaltine sulfide systems, and maybe you have more ideas in these things. And they should all produce very large spin Hall and Edelstein effects. So these systems can be quite useful for our experiments, and we are still trying to learn, and it's very useful to investigate those properties. And with that, I want to summarize what I showed from our lab. The results are this graphene can be good system for spin transport. There are other 2D materials like boron nitride, good tunnel barrier. You can make heterostructure to manipulate or control the spin polarization. And we can see the spin galvanic effects, magnetic proximity effects in these structures. And one can study the spin charge conversion in topological materials and also Weil semimetals by making such heterostructures. So most of the things are focused on understanding the systems and what we can use for real devices. But we are not in the realistic world. So everything can be like you see topological insulators should be like this, but really that may be not the case when we make the device. So that is all contributing to the understanding and future development in this direction. Okay, with this, I would like to thank you for your attention, and we can take some questions.
Thank you, Saroj, for this excellent talk and highlighting all the key developments in this field, and especially your last statement, I think is quite important that to take into account when we go to devices, things are very different. It might be far from ideal. So, any questions? I think there was a question from 20 minutes back. in the last session. That do you have a RT plot in different field for BSTS?
You have a RT plot in different field. Okay, with you mean the different magnetic field? Yeah, so I don't have that, but people have done that. In literature, you will find lots of example. So when you apply a magnetic field, sometimes you also make it a bit more insulating. You open gaps and break also symmetries. So you can send me an email. I can send you some literature on that. So there is lots of studies on that also.
Any other questions? There is one.
What information about the bulk can one obtain from surface transport measurements? TI is also, is it possible to directly measure such bulk properties? Yeah, so you know from your material, if you do, for example, when you grow a material, what people have to do is, let's say, do basic studies. Um, Everybody cannot do a RPS measurement because it's very special. Of course, you can send your sample for RPS measurement to check whether there is a bulk and surface state and as it should be look like. But when you make a device, what we can measure is the resistance. Resistance measurement. um Let me read your question again. What information about bulk can one obtain? Yeah, so if you see metallic behavior, so like resistance decreasing when you decrease the temperature, so that means it's mostly coming from the bulk. If we are considering about the topological insulators. And if the resistance first increase, like semiconductor, then the carriers from bulk freeze out below some temperature, you can find more topological surface state behavior. So, only, yeah, you have to consider where we are. So transport experiments actually it mix of everything. So you have to go to some regime where you think bulk is dominating or surface is dominating. There you have to do the experiments, magnetotransport or other kind of things to find out that property. But there can be regime where both contributing together. So in that case, so you have to also, you can do that by doing some angle dependence measurement of your weak anti-localization, and also that also can give whether it's a bulk property or surface property. And there are lots of studies about that as well. If you are interested, maybe send me an email. I can send you more links about that. Yeah.
There's another question here. What is your perspective view on CO3SN2S to magnetic wild semi-metal? We have good quality single crystal of CSS available with us.
We have good, okay. Let me go back. Yeah, so this is a magnetic, it's a magnetic semi-metal. And yeah, so this can be interesting because as I told, it gives very large anomalous Hall effect. And spin charge conversion also in this material can be very large. But for making devices, so bulk material people have studied, and to make devices actually we need thin films. So that can be challenging. Or if we can find who can do some focused ion beam cutting of sample, so that can be also, with that we can also make devices. But it's interesting that you have such crystals. So maybe we can discuss about that. So just send me an email. And these materials are very new, and I don't think many things have been studied. Yeah.
Any more questions? You can raise your hand. I mean, if you have a big question to type. Right. I don't see any further questions now. So yes, from my side, I would like to thank you once again for this excellent talk. I mean, it was very sort of comprehensive and reviewed all the current developments, starting from Spintronics and GMR. So thank you very much for that. And to the participants, we'll be sending you the links to YouTube for this video. And before I hand over to Professor Ratnamala Chatterjee for a few concluding remarks, I'd just like to point out that the next talk is on 3rd and 5th of March. We are going to send you the links, but please note that the time is different. So the Indian Standard Time is 10:30 in the morning to 12:30 noon. So that would be very early morning here in UK. So I think people can view the talk in YouTube. That was the only time available because the speaker, Professor Sumanta Tiwari, is in the US, and that was the only way we could coordinate because these are 3 different time zones. And the title of the next talk is Topological Superconductors and Majorana Fermions in Condensed Matter Physics. So we're looking forward to that talk, and we hope to see you there. And I'll now hand over to Professor Ratnamala Chatterjee to conclude this. And thank you to Professor Saroj Dash from my side.
Thank you.
Thanks, Saroj. Last moment pe I had actually the DDSNP called, so I had to rush out. So
okay, it's fine.
I missed the last part, but it's okay. I'll hear you once again sometime.
Yeah.
So
I just tried to give a experimental perspective. So
yeah,
as you see from my talks that we are not in the very beginning of the developments. So we pick up things where it's bit known that we can make some devices out of that. So we are in the middle somewhere.
Yeah.
Then from our research, some maybe people are watching which will be useful from our part, they will pick up again for developing for applications. So we are trying to bridge the gap between basic science and applications. So I hope I covered some
that is the
from an
beautiful
experimental perspective, something. Yeah.
No, that is the beautiful thing that you have done, and I can see that you are trying to also use these Fermi pockets, wave pockets, which is where some of our results are also pointing out. I'll share with you later that we should be possibly, and in these pockets we find that mobility of the carriers increase immensely and the number of charge carriers also increase. Do you see some, I mean, you have been able to use that fact?
So when you tune the Fermi level, you mean mobility goes up. Yeah,
Mobility,
that should happen.
yes.
Yes.
Exactly, in these Fermi pockets.
Yes.
And also the effective mass of the fermions in this is very small compared to the electrons mass.
Yes, yes, yes.
So that we get from
that we extract from Subnikov has, I guess.
Yes, SDH. SDH, that is what. So are you also able to see the ease of movement of these electrons?
We have not done such systematic measurements. Yeah, so yeah, I don't have such data yet.
But maybe we can do it together. Maybe Vishal can do it. You can ask him.
Yes, yes.
He can do it. So, oh, that's very nice. So I look forward to working with you, hopefully, in near future. Yeah. Chalo, all the best.
Yeah.
And is the talk over now?
Yes,
Oh,
the
okay.
talk is over.
Okay.
So I'll
you are
stop
going
recording.
to, okay, I have got the recording of Saroj's first talk. So I guess you will be uploading it together, is it?
Yes, we are going to upload. So yeah, Ali will upload both the talks in YouTube, and he will be sending the links to all the participants. Yeah.
Very nice. Very nice. So Saroj, you know the next talk is by Siddharth Parmeswaran. So
Please
maybe
send me the
that day
link.
if you are free.
Miladi. Yeah.
No, the next talk is by Sumanta Tiwari, and the
Oh,
last talk
next
is
one
by
is Sumanta
Siddharth.
Tiwari. Yeah, yeah.
Yes.
So
Yeah.
he is also a very good speaker. So
Yes.
Saroj, if you get time, if it is matching with you, otherwise you can watch it on YouTube
Yes.
when we
Yeah,
upload.
that is.
Yeah.
So I think if students will also learn more theory